All right, we're on resource. All right, this is a good moment. Okay, falling elevator. All right, so it's going to be a conceptual regarding this one. This was a mind twister, and hopefully you guys will be able to answer this question this time around. Okay, this time I want to know how this guy ended up breaking his neck. Okay, last time I asked whether or not it was possible for this person to go off to the ceiling. All right, so a lot of you guys initially thought that when the cable snaps, all right, so here's an advanced storyboard. Let me take you through it one more time. A lot of you guys mistakenly thought that the person initially went up to the ceiling, and then the person hits the ceiling, and it falls back down to the floor. So either the first or the second impact is going to break his neck, right? So that's what most of you guys thought. Reality of it is that's not at all what happens. The person is going to remain on the floor at all times, and the reason is because free fall, right? Something that Galileo came up with. So the person inside is falling under the influence of gravity. Elevator is falling under the influence of gravity. And when things are falling under the influence of gravity, everything is going to fall at the same rate. Everything. Person inside in the elevator. So the person remains on the floor at all times, except the person will not be able to feel the floor under his feet because the person will become suspended relative to his center of mass. So everything falls at the same rate. So there's a safety system that catches the elevator, brings the elevator to stop very, very gently. Yet you got a person who's got a broken neck. So how's that possible? How's that possible? Damn it, there's a safety system that catches the elevator. Safety system, it brings it to a stop gently. Like the giant drop from Six Flags or the Tower of Terror at Disneyland or Disney World. I don't know which one. All right, so despite the safety system, there's a person with a broken neck. So the question is, is this scenario even remotely possible? The answer to that question is absolutely. Absolutely. Yeah, you can break your leg, you can break your arms, you can break your back. You can break just about every single bone in your body despite the safety system. So the only thing that I'm going to ask you is come up with one single scenario, not two, not three, not five, just one single scenario to explain how this could be possible. Well, it depends, right? It depends on what you will do when you find yourself in a falling elevator. What would you do? You're feeling weightless. Imagine that you're like 2 steps away from the handlebar. What would you do if you didn't know physics? Oh, you're thinking, I've got to balance myself. So it would be awesome if I could just walk towards the handlebar so I could just hold on to it. Question, can you actually walk inside a falling elevator? Another thing that I hear is, oh, you would jump. When do you jump? What difference will it make? Can you even jump inside a falling elevator? And even if you did, what do you think is going to happen? If everyone comes from high school physics teachers, one of the worst advices that you could ever hear, they always say, just lie down on the floor, lie down on the floor. Why? Because they say you can just spread the impact force onto a larger surface area. I don't understand. I don't understand the logic behind it. Man, there's a safety system. You don't think your body can handle 2 Gs or 3 Gs? You think that you're that fragile? So what's the big deal? Can you even lie down inside a falling elevator if you're caught in the middle? If you try, how would that work out? One thing that you need to remember is you will become suspended.
I've only experienced tiny.
You will become suspended relative to your center of mass, just like that. So the distance between your center mass and the ground floor is going to be fixed. This is it. You cannot be falling. You're not falling any faster than the elevator, so this distance is going to be fixed. You can move relative to your center mass. That's it. You can turn this way relative to your center mass. You can turn that way relative to your center mass. You can turn this way. You can angle yourself this and that. All right, so first question, can you walk inside a falling elevator? Absolutely not. Why not? Because where's the friction? For you to be able to generate friction, you need to be pressed up against the floor. You cannot even feel the floor under your feet. All right, so which means that you're applying no force on the floor, which means that the floor is applying absolutely no force back on you. So you cannot walk. What would happen if you tried to walk? When you try to walk, what's going to happen is your body is going to start to go out of alignment as you're trying to walk. So you're going to start to move relative to your center mass, side to side, side to side. And as you're doing that, what happens? Well, at some point, the safety system kicks in. Your body is out of alignment. What do you think is going to happen? You will fall. Potentially, you will break something. Jumping out from the floor is not an option either because in order to jump, you have to bend your knees. When you bend your knees, you're losing complete contact with the floor. You're not in contact with the floor, but obviously you're increasing the distance, so that's not going to help. You can push against the floor by extending your feet, stretching your feet. It's going to give you a relative speed. Relative to the elevator, you will gently go up to the ceiling. You will float to the ceiling more like it and hit the ceiling very gently, and then you will bounce back down and you float towards the ground. All right, you don't want to be a floater inside a falling elevator. You don't want to be going up and down. All right, that's like one of the worst things that can happen. You have no control over what's going on. Under the circumstances, you got to remember it's dark inside. You're feeling weightless. You're floating all over the place. You could be upside down. You could break your neck. Another thing that people try to do, if you try to get yourself body parallel to the ground, so what you need to do is you need to bend your knees and then pull them in towards your chest. It can give you a slow rotational speed. You will be spinning like a spinning top, which you don't want to do instead of falling under. So any of those will potentially cause an injury, any of them. All right. Every time you move inside a falling elevator, your body's going to get out of alignment. You're not going to be able to get down on the floor. Obviously, you cannot get your body parallel to the ground without touching anything. Jumping is out of the question. So the best thing to do is do absolutely nothing. In the worst case scenario, you may end up letting yourself like that you can live with. All right. That's actually the best thing to do. Even that may not work because look, when the elevator goes in a free fall, you will feel weightless, right? And then when the safety system kicks in, it's got to be 2-3 G's of acceleration. So you will go from feeling weightless to 2 or 3 G's of acceleration. You may still end up losing your balance. Most people would. Okay, so potentially you can still break a bone. So I gave you guys 4 scenarios as to how a person inside can have a broken neck. All right, 4 scenarios. Pick and choose, and then think about it because it's a tough question. All right, so we'll have a bunch of questions regarding this, a bunch of multiple choice questions as well as conceptual questions. All right, so gravity gives you a weight. So the amount of gravitational force acting on you becomes your own body weight. Obviously, you can lose weight by using mass, diet. Your weight is going to depend on where you do the measurement. On the moon, for example, you will weigh 6 times less, so you're going to be 6 times lighter. On top of a very tall building, like the Sears Tower in Chicago, slightly less. 30,000 feet up in an airplane, it's going to be about 2 pounds less. So the weight is going to change. So one of the questions that we will tackle is this question. Everything falls at the same rate, right, in a vacuum? So the question is why? All right, so why is it everything is going to fall at the same rate in a vacuum? So the falling objects will accelerate at a constant rate. So the question is why? I'm asking the same question twice, believe it or not, right now. That's it. Everything falls at the same rate. Why? All right. Why is it everything falls at a rate of 9.8 meters per second squared, probably about 10? So what causes it? So what is the nature of gravity? Is gravity a force? And then the next question is, the alpha falls because of gravity. Does gravity also extend all the way out to the moon? Okay, so we had an argument that it might, but where's the proof of it, right? All right, so here's what we came up with initially. So we said that the gravity is a force because gravity does exactly what a force does. It causes acceleration, right? So the falling objects accelerate under the influence of a force, and the falling objects will accelerate at a constant rate. And then you can trace the force out to the source because the acceleration and the force will be in the same direction. So you notice that the force is originating from the center of the Earth itself. We also know that there's a force going all the way up to the moon because if it didn't, the moon would have gone in a straight line at a constant speed. Instead, the moon is orbiting the Earth. All right, so direction, speed is constant, but not the direction. So the direction is changing, which means that the velocity is changing. And you know this is circular motion, so which means that the acceleration is directed inward towards the center of the circle. And obviously, you can all of a sudden you discover that the origin of this force is also the center of the Earth itself. So naively, you add 2 and 2 together. You say the force pulling the apple down must be the same force extending all the way out to the moon. Okay, so that's an argument. This is a connection that you make in your mind immediately. But as soon as you make that connection, notice that there's some problems with that connection. The problem is the apple falls. How come the moon is not falling if that's the case? In all appearance, the moon does not fall. All right. So if the apple falls and if gravity extends all the way out to the moon, why does it the moon fall? So that was a question that we had. In modern days, obviously, we send people out into space, right? And then as soon as they get to space, these people appear to be weightless. You know, you get your weight from gravity. So the question is, wait a minute, if gravity extends all the way out to the moon, can you be weightless in space? People will say, no, you can't be weightless in space. In fact, people will say, just about the only place in the universe you might become weightless is deep, deep, deep space. You might means there's no place in the universe where you will become truly weightless. That's what it means. All right. So if gravity extends all the way out to the moon, there's absolutely no place between here and the moon where you should become truly weightless. All right. And the net force acting on you at some point becomes 0, but that's near the moon, but you still weight. All right. So in order to answer these questions, once Newton establishes that gravity is a force, now you have to come up with a theory to explain how this force comes into existence. He figures that the force is going to be directly proportional to the product of the masses because masses will attract each other through gravitational force. And he reasons that the force is going to diminish with distance as measured relative to the center of mass as the square of the distance. And capital G represents the strength of gravity. So F is the force of gravity. You got small mass, big mass. R is the distance. Just remember the distance is going to measure relative to the center of mass. Capital G is the universal gravitational constant. It's going to give you the strength of gravity. So it's a very small number. You got 10 zeros before the first number. And that's it. That becomes the law. All right, so the question is, does gravity extend moving out to the moon? All right, question of, why is this constant? Why is it everything falls at the same rate? Why is it that the mass of the falling object does not matter? Newton's explanation is straightforward. It's very elegant. All right, he kind of cuts through the philosophical BS because he knows that this is a mystery. He himself doesn't know how to explain it, but he knows that the weight is going to be provided by the force of gravity, right? So the gravitational force acting on this apple is going to give it its weight in essence. So here's the equation for weight. Here's the equation for gravity, gravitational force. So the weight and the gravitational force are the same because gravity is what gives you the weight. So all of a sudden, he's equating the right-hand sides of the equations to each other, solving it for g. So the mass of the apple doesn't matter. So it's going to get canceled out of the equation. And that comes up with an equation. Now, the distance between the apple and the Earth is going to be measured relative to the center mass, from the center mass of the apple to the center mass of the Earth. So for all practical purposes, that's going to be the radius of the Earth itself, right? All right, so he comes up with this equation. All right, so according to this equation, if it's correct, how fast the objects fall will depend on the mass of the planet, and it's going to depend on the size of the planet. All right, there's an interesting relationship here. All right, so before we explore that relationship, let's check to see if the formula is correct. So here's a measure value, and we'll get the predicted value from the formula that you just saw. The predicted value and measure values are the same. So what that means is this formula is correct. So once we know the formula is correct, so which means that this formula correctly represents reality. That's what it means. All right, so which means that how fast the objects will fall depends on the mass of the planet. It's going to depend on the square of the size of the planet, but the relationship is an inverse one. So for a given size, if you find a planet which is 2 times larger than Earth, gravitational pull is going to be 2 times larger. For a given size, if you find a planet which is 5 times more massive, G is going to be 5 times larger. Okay, now we got the counterintuitive predictions going on here that we need to focus on. All right, so smaller the radius for a given mass, larger than gravitational pull is. That's what it means. So you find a planet which is half the size of Earth, it's got the same mass, half the size. Gravitational pull is going to be 4 times larger. You find a planet which is 3 times smaller, so which means gravitational pull is going to be 9 times larger. All right. Find a planet which is 5 times smaller for a given mass, so which means that you take the Earth, start shrinking the size, make it 5 times smaller. Remember, 5 squared is going to be 25, so it's going to be 25 G environment. Okay. Okay, so one of the things that you need to notice is Newton's theory really does not explain why the mass of the falling object does not matter. It provides no explanation for it. Okay. It just gives you a mathematical prediction as to what the relationship is between mass and the gravitational acceleration and the size and the gravitational acceleration. That's it. It describes gravity. It does not explain it. All right. So we didn't know why the mass of the falling object didn't matter before we did the derivation. We still don't know why the mass of the falling object does not matter because it simply got canceled out of the equation. Newton's theory does not explain how gravity works. It just describes what gravity is. It's a descriptive physics. A lot of the classical physics is very descriptive. You may start doing the math because you have a lot of questions that you want answered, but by the time you're done, you only have a mathematical model that's describing what it is that you were trying to resolve, and you're not going to be able to. So physics is kind of weird like that. All right, so you're not able to answer every single question, but regardless, there's still a really good relationship that you can explore. So, meaning that this theory makes some interesting predictions. Meaning that if you find a planet which has the same size, more massive than Earth on that planet, you will feel heavier. Okay, so that's a prediction. If you find a planet which has got the same mass except 5 times smaller, you will feel 25 times heavier on that planet. So before landing on that planet, just think about it briefly because you could get yourself crushed to that. That's what it means. It makes predictions. It makes really good predictions. So it's more of a mathematical model. So how did Newton know that his theory was correct? Well, he must have called the psychic hypothesis. So how do you know your theory is correct? It's straightforward, guys. How do you know that? You just check it against reality. Okay, so here's the predictive value. Experimental value is the same as the predictive value, so that's how you know. Nothing else. Next question. Gravity extends all the way out to the moon. Well, you know something does. There's some kind of force extending all the way out to the moon. And the force appears to be originating from the center of the Earth itself. So the question is that gravity? All right, so if the force extending all the way out to the moon, originating from the center of the Earth itself, if it's gravity, this would be the acceleration of the moon at that distance. So if the acceleration here is caused by gravity, it should have a value, a measurable value. Measurable value is going to be 0.0027273. Okay, so 0.00273 would be the acceleration of the moon. All right, here's the predicted value. So somebody had to go out and measure it, obviously, if the measured acceleration is the same as the predicted acceleration, then which means that the force extending all the way up to the moon had to be gravity. No such luck. This guy lived 350 years ago, so there was no way to measure an acceleration, which is this small for a distance of 250,000 miles. Instead, somehow, magically, they were able to measure something else. All right, so they noticed that the moon, instead of going in a straight line, it would deviate from a straight line towards the Earth, a distance of 1/20th of an inch per second. All right, so that's what they were able to measure. So this is what Newton wants them to measure. This is what the astronomers were able to measure. So now it's Newton's task to figure out how he could come up with predictions regarding this deviation from a straight line towards the Earth within 1 single second using mathematics. All right, so now he needs to come up with a predictive value using this calculation that he came up with. Anyway, so he invents calculus. Out of calculus, comes up with this equation. This is a free fall equation. So this is the distance fallen. Theoretical distance fallen is going to be this. G is going to be that value. So if you take this, the predicted value, plug it in, if the time is 1 second, would you get a 1/20th of an deviation, 1/20th of an inch deviation from a straight line? If the answer is yes, then the predicted value is going to match the observed value that you're looking at. So, boom. So you do the substitution, everything goes in, boom, 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 and then he gets a 1,000th of a meter, which is 1 millimeter, roughly about a 20th of an inch. So here's the theoretical value, the predicted value, and here's the observed value. So the theoretical and the observed values match. So this 1/20th of an inch deviation from a straight line that he himself was able to get out of his calculus matches the observed 1/20th of an inch deviation from a straight line. So here is the proof, ladies and gentlemen, that gravity extends out to the moon. And the guy was able to do this.
Most of us have only experienced a tiny.
All right, so this guy is either there's a space lab station, that's not possible. The first thing you need to figure out is you're really weightless. For really weightless, location, the acceleration is 0. And not the D, I get smaller distance. So I get the distance to the station.
Hey, you're sounding weird right now.
Thank you. Is it better or worse?
It's better.
Is it better? Okay, I just want to make sure. All right, guys, I appreciate the feedback. Just let me know. And also, I appreciate the fact that some of you guys showed up because, or else it feels lonely when I'm doing these recordings. It's not the same. All right, so, I mean, you're 180 miles from the surface of the Earth, right? All right, so closer you get to the surface, the larger the gravitational pull is. Further away you are, weaker it's going to get, obviously. So if it's 0, then you're weightless. If G is 0 in space, you're weightless. Or if you're like microscopic, then you can call it microgravity, like the way NASA calls it microgravity. In reality, it's neither. G is not 0, and it's not micro either. Micro means 10 to the minus 6 something, okay, meters per second squared. It's not microgravity. Being in space, anything, you will weigh 15 to 20 pounds less. Okay, you're not weightless, you feel weightless. That's what it means. You appear weightless, you feel weightless. So the question becomes why? Why is it that if you're not weightless, you feel weightless? All right, Newton provided a beautiful explanation for it. And this is an reinterpretation of what Newton came up with. All right, so imagine you're at the surface of the moon, you got this rifle, you can just keep firing bullets at varying speeds. And then the bullets will fall in the form of projectile motion, which is a form of free fall. All right, so 3 bullets fired at the same time, end up landing at the same time. Okay, something that we discussed before, because everything falls at the same rate, regardless of their horizontal motion, right? It's called free fall, because everything is falling under the influence of gravity. But you can keep firing bullets, and faster, the faster the bullet is fired, the further away it's going to travel. Now, at some point, it's going to go so fast that the trajectory of the falling bullet is going to match the curvature of the surface of the Earth. That's what it is. So unless she takes a step sideways, she's going to take a bullet to the back of her head, because this bullet is set to be in orbit around the moon. All right, so notice that the orbital motion is the same as projectile motion, except in this case, the object is moving so fast that the trajectory of its motion matches the curvature of the surface of the planet or the moon 100%. And you know that the projectile motion is the same as free fall. And you also know that in free fall, like finding yourself in a falling elevator, you will feel weightless, because you and the elevator are falling at the same rate. Likewise, the person inside the space shuttle is in free fall in the form of projectile motion. This person is standing on a scale feeling weightless. This person is standing on a scale feeling weightless. This person is not weightless, neither is this person. It's just the appearance of weightlessness is what these people are experiencing. So in space, you have the appearance of 0G or microgravity, but it's not, G is not 0 and gravity is not microgravity either. All right, so Newton's obsession was once again, he said if the apple falls because of gravity, why doesn't the moon also fall from the sky? Guess what? The moon also falls, just like the apple does. Except it falls in the form of projectile motion. It falls from a straight line, 1/27 inch per second towards a trajectory that matches the curvature of the surface. The moon also falls, just like the apple does. Ooh. All right, so question about levitation. And there's going to be a question about levitation at some point. Is human levitation possible? So answer that question is no. And then there's going to be a question about the levitating monk. I'm going to focus on that one. Okay, so I'm going to make the argument because I'm just going to naively make the argument that in order to levitate, you have to overcome gravity. And then I'm going to naively make the argument that you have to overcome the strength of gravity. Okay, so this is microscopic, right? So you got 10 zeros before you hit the first number. I play a little bit of mind games with you guys. I say, look at the size of this number and look at the penny in your pocket expressed in terms of a dollar figure, right? So this number is way smaller than a penny in your pocket. So if you got less than a penny in your pocket, what do you have? Nothing. So can you overcome something which is less than nothing? That's a pure mind game, right? It's psychology. It's what politicians do. It's reinterpreting the facts, all right, and playing mind games. And everyone is susceptible to this sort of stuff. And if you got fooled by it, it was intentional, all right? So my job is to educate you guys, obviously, just to make sure that you understand that you're susceptible to these kind of mind games. So the impression is, here's the strength of gravity. It's a small number. Gravity is the weakest force. And the number is smaller than microscopic. You got 10 zeros. Mind over matter. Can you overcome something like that? All right, so the next thing you know, I set up the lecture in such a way that I made some references to Tintin, and the author, the artist, or whatever, it evidently was basing all these things on his life's experiences. And then next thing you know, you got a monk who looks exactly like, kind of like the monk levitating. All right, so when I was designing the lecture, I made sure that I gave you what you were looking for, which is everything that you see is a hose. All right, you got these levitations and all that stuff. You got a levitation stick. People are doing the different versions of the same thing. And all of a sudden, this guy is fully levitating. All right. Number one, he's not a magician. Number two, he said, I don't want to do it. So he had to be convinced to do it in front of the cameras. And number three, he says, it's just a part of his yogic practice. And he's got a reputation for it. It's a beautiful levitation. It's beautiful. So he's not touching the ground. The magician is checking to see if there are any wires. He's not able to see anything, blah, blah, blah. So my question is that true levitation?
For that, I think there.
All right. Is that true levitation? I don't know how he's done it. It's impressive as hell. Okay, I have no idea how he's done. Is this true levitation? Absolutely not. Why not? Because if you could just cancel out gravity, you would not be hovering around just like that. Remember, guys, if the Earth is spinning on its axis, right? You're moving with the Earth at 1,000 miles per hour, give and take. You will keep on moving in a straight line at a constant speed. So from your perspective, because the Earth is curved, you would see this person rising up towards the ceiling at an angle. All right, you can't just put the brakes on like that. It's out of the question. It's out of the question. So it's not true levitation. So that's one of the answers that you can come up with. There's more that you can come up with. All right. Another thing is this capital G that you're overcoming, supposedly this is the strength of gravity. Take the strength of gravity, multiply by the mass of the Earth, and divide it by the radius of the Earth. It's going to give you a number which is roughly about 10. This gets multiplied by your mass. It's going to give you your weight. My weight is like 150 pounds. How do you overcome 150 pounds of weight, mind over matter? All right. Only way you can overcome it by generating an external force. You push up against the ground will have to apply the same force back on you. If there's such a thing as a spiritual uplift, or using the vernacular that my dad uses, the holy force, it would be an internal force. It would not get you to, it would not lift you up from the ground. There's no such thing. All right. So just be aware of it. Those are the explanations that I'm looking for. I'll edit this out so it's not a big deal, but you wasted like minutes. All right, so let's go.
Having to plan. It's while tethered to the cable.
All right, so a couple of things here. Now PowerPoint is working. All right, so this is something that your test problem, this is for college physics students, is going to be related to this. Okay, so how do you compute the tension if the mass and the speed is known? All right, so that's the problem that the college physics students need to focus on, because it's not a complicated enough problem. Mathematically, it's not that involved. I just want to go easy on the math from now on for college physics students, because you guys are getting into medicine or biological sciences or whatever. It's about time to go easy on the mathematics. Okay, so that's the question that you guys will have to focus on. For university physics students, this is one of the options, one of the problems, because there's a lot of There's some good
Speed is
stuff that I
critical.
can
I
do
need
with
some.
this one. Okay, so in order to loop, how fast do you have to go? All right. I gave you a standard solution, but you have to practice it. There's enough room there to ask really good questions. So, okay, so the two things that we're going to look at some point. All right, so here's the centripetal force formula, Here's the centripetal acceleration, so it's going to be squared r. The examples, rotor is a centrifuge. You're suspended on a wall. All right. So what is the centripetal force in this case? Translated in English, what is the force? Actual force, which is directed towards the center. All right, so that would be the normal force, right? Because you're pushed against the wall, and the wall is preventing you from going in a straight line at a constant speed. So, which means that there's a push from the wall that points towards the center. So that becomes the centripetal force. Space shuttle orbiting the Earth, or any shuttle orbiting the Earth, or the satellite orbiting the Earth in this case. The force directed towards the center of gravity. Car negotiating a curve, the force directed towards the center is a frictional force. So those are a bunch of examples of. So centripetal force is any force which is directed towards the center of a circle. All right, and here's the generic expression for this centripetal acceleration. So which means that every time you see centripetal acceleration, you have to substitute that formula in it. So here's a generic expression for the centripetal force. All right, so centrifuge, mass is suspended in it, centrifuge is spinning in this direction. So in this case, the centripetal force is the normal force. Satellite orbiting the Earth, the centripetal force is gravity. So you have to use the gravitational force formula for it. And the car negotiating a curve, the centripetal force in that case is going to be the static frictional force. All right, so those are the cases that we'll look at. All right, so lecture reading material. How do we know that gravity extends all the way out to the moon? You know that because number one, if it didn't, the moon would have gone in a straight line at a constant speed. You also know that the moon is accelerating, right? All right, so if the gravitational force acting on the moon suddenly and magically vanished, you would be moving in a straight line at a constant speed. The moon would be moving in a straight line at a constant speed. All right, so the force of gravity is going to be related to the product of the masses. So that means multiplication. It's going to be inversely proportional to the square of the distance as measured relative to the center of mass. And universal gravitational constant is just a very small number. It gives you the strength of gravity. Everything follows at the same rate. The g is constant because the acceleration due to gravity only depends on the mass of the planet. It's going to be inversely related to the square of the size of the planet. All right, so if you were to, let's move forward. If you were this, I don't want to spend any more time right now on this move. All right, so you find a planet, same mass, half the size. All right, so smaller the radius is, the bigger the g is going to be. So the radius is twice as small, gravitational pull is going to be 4 times as large. Newton knew his theory was correct because experimental and theoretical numbers match. That's how you know the theory is correct. In the making of the movie Apollo 13, the actors appear weightless because they were experiencing free fall in the form of projectile motion inside the airplane. All right, so if you bring a space shuttle closer to the surface of the Earth, just like that, gravitational pull is going to get larger. All right, so closer the space shuttle gets to the Earth, stronger the gravitational pull is going to become, the faster it needs to move. All right, so we got a space station orbiting the Earth. All right, so it's got no actual gravity. So you got a book on a tabletop, slide the book across, will it experience any friction? The answer to that question is no, because it does not have any apparent weight. So what that means is the book and the table are falling at the same rate, though the book is right at the tabletop. It's not touching the table. That's what it means. Everything is falling at the same rate. All right, so it's not touching anything. Is human levitation possible? No, it's not possible. Once again, you think that this is the number that you need to overcome. This is the strength of gravity. So by the time you're done with the computations, the mass of the Earth, the size of the Earth, and all that stuff, you will get a g which is about 10. And then 10 multiplied by your mass is going to give you a weight. You cannot overcome your weight by an internal force. Internal forces will not cause acceleration, even if there is such a thing as a spiritual uplift because it makes you feel good. You're not going to just boom, start levitating. It's not going to happen, right? Everything that you see is a magic trick or an illusion, so it's not possible. Even if you could levitate, the only way you test it is check to see if the person is still rising. If this monk started to rise up towards the ceiling, I would go, oh, something is wrong with physics. I'm fine with it. If it's true levitation, I'll say, okay, so evidently there's something I'm not understanding. Maybe that spiritual uplift at that point is just an external force. It's like the angels are just pushing me in that direction or something. I don't know. I would go, okay, so there's something happening. I don't see that. The only thing it looks like, hey, it's a magic trick. I don't know how he's done it. Like I said, I'm impressed. I like being fooled, but not to the degree that I'm going to think that this is real. All right. All right. So I like the magic of the magic shows. All right, so some yogis claim that they feel weightless while they're hopping. Well, the reason is because these guys are going through projectile motion, which is the same as free fall, blah, blah, blah. All right, so if you're suspended on a wall of a rotor, centripetal force is the force which is directed towards the center, which is the normal force. Satellite orbiting the Earth, so that's the same as gravity. Car running a curve is the static frictional force. Okay, so those are the basic. All right, so the weight of a car, does that matter? How fast the car can negotiate a curve without going into skid? No, it's not going to matter. All right, this is for university physics students. Okay, guys, this is the problem that you will have to focus on. Okay, so there are two problems that I'm gonna let you focus on. One of them is looping the loop. The other one is car negotiating a curve. And I'm gonna tell you what to focus on shortly. All right, so what else do we have? Okay, good enough. Let's move on. All right, so this is one of the problems that you guys need to focus on for university physics students. This one is somewhat involved, but it's not bad. It requires practice and practice and practice and practice. And then I'll give you a little bit of a hint. I'm not gonna give you a little bit of a hint. I will do a little bit more than that because I really want you guys to practice this. And you guys will have to take engineering dynamics at some point. This is the sort of stuff that you will get to do tons and tons of times. So it's high time that you start learning how to do these kind of problems. Okay, number one, there won't be any numbers involved because real physics is done boom, 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 symbolically. So does the maximum speed of a vehicle while the car is negotiating a curve without going into skid, will it matter? Does this mean that every vehicles need to go slower if they don't want to skid? All right. You will get a numerical version of that. All right, so speed is what we're trying to figure out. All right, and circular motion, I know that the centripetal force is going to be the static frictional force. So what you need to do is just make sure you have a diagram. Okay, just make sure you have a diagram. Man, this is classical physics. If you don't have a diagram, I don't care how many times you practice this. I'm going to force you into an operator. Okay, make sure when you are doing a problem, your solution is coming out of the diagram. You need to have a force diagram. If it's circular motion, make sure that circular motion is there. All right. Centripetal force is the static frictional force. All right. At the maximum speed for negotiating a curve, once you reach the maximum speed, at the maximum speed, you're maximizing the static frictional force. The tires will start to screech under the circumstances. All right, so I'm interested in the speed, the maximum speed. And I know that the generic expression for the centripetal force has the speed in it. And that's the reason why this is my starting point. I say a centripetal force is the static frictional force. Okay, so that's how I start. And I say, oh, this the centripetal force is the speed that I want in it. And here's a mathematical expression for the maximum static frictional force. All right, so you know that this will equal to that. All right, so I'm isolating V because V is what I'm looking for. Immediately, you notice that the mass doesn't matter. It just, on the left-hand side, you got canceled out of the equation. Okay, I just said it wrong, but that's fine. And all of a sudden, your initial impression by looking at the right-hand side is speed and the mass will be inversely related, which means that the more mass the vehicle is, the slower it needs to go. And then you're thinking, I'm done. When you're symbolically doing it, you may think that this is the way it is because you don't see the initial conditions. The numbers are not there. Being a physicist, though, I don't need to know the numbers. I have a feel for what's going on because I know that this is going to be a number. I know this is going to be measured. This is also measured. Mass is also measured, but N is not measured. N is a reaction force. It's a reaction force to whatever the mass does. In essence, it's because mass got inertia, guys. So you can apply a force on it; it turns into weight. If something is moving to begin with, it's going to want to move in a straight line at a constant speed. So it's going to cause all sorts of reaction forces. If it's in motion, if it's not in motion, it's going to cause reaction forces. So I know that N is going to be somehow related to this, but I know that because I've been doing it for 20 plus years, guys. It just you kind of get an intuition for it. So all of a sudden I go, oh, so we need to figure out what N is. It's a reaction force. So now I have to do a force diagram. All right, so all in the y direction, it's got weight. So the weight is going to be responsible for N. So what I need to do is instead of saying N and weights is the same, I'm just going to let mathematics take care of that assumption. So I don't need to, unless I have to make assumptions, I will not. If the math is going to take care of it, let math take care of it. So sum of the forces along the y direction and is up, W is down. There's no acceleration along the y direction, so this is going to be 0. So N is the same as W. Do a back substitution. Okay. And all of a sudden the masses will cancel. And the only thing that matters is the quality of the tires. Higher quality vehicles with high quality tires will be able to negotiate it faster. And that's it. All right. In engineering design, the only thing that you get to control is R. All right. So you will figure out what this speed limit that you want for that curve is. And based upon that, you figure out what R is going to be. The rest is up to the quality of the tires. Okay. So maximum speed at which the vehicles can negotiate a curve does not depend on the mass of the vehicle. That's the only thing that you can conclude out of that. All right. So for engineering for those of you guys who are taking university physics, you will get to do the same problem, except there's going to be an angling implant. There's going to be an angle involved. All right, so which means that the road is going to be bent for this one. Okay, so how do you do a problem like that? Look at my solutions. There's an example problem. All right, so that's the one that you need to practice in essence. Find problems just like that. This is slightly more involved. This is like your homework. I'm going to be testing you on it. I'm going to give you a problem for related to the maximum speed required for you to be able to negotiate a bank road or whatever. All right, so that's the way it's going to be. So make sure that you're actually doing problems regarding this, and also make sure that put the numbers aside. Okay, just do this stuff exactly the way I'm doing it. All right, so just keep your work as clean as possible symbolically and explain. Make sure that you're aware of every single assumption that goes into it. By the way, a problem like this cannot be done unless you draw things out. And then how it's going to be done is going to 100% depend on how you set up your coordinate system. All right. One thing, how you set up your coordinate system is going to matter or something like that. So look at my solution and find problems similar to those. Okay. You either go to the library, check out a book, find some physics books, PDF versions of physics books, and just go over some problem, because this is the sort of stuff you need to practice. Welcome to university, by the way. Yes, I'm not a teacher, I'm a lecturer. I always say that. Your job, I just make it coherent. I put the stuff out there. It's your job to learn it. This is not a higher teaching institution. It's a higher learning institution. All right. I give you feedback. I give you directions, this and that. I explain stuff to you. The rest is up to you. Just get used to it. It's not high school. It's not an extension of high school. This is real life. If you're a little bit confused, just work harder, ask for more feedback, ask for more direction. And that's the only thing that I can do. All right. I can just lecture, I can do a little bit of coaching, and the rest is up to you. Welcome to real life. Welcome to adulthood. For those of you guys who are still coming out of high school. All right, so that's one of the things that you need to focus on. All right, for college physics students as well as the university physics students, okay, this is for both of you guys. If you have multiple forces acting along the radial direction, forces towards the center is going to be positive, forces away from the center is going to be negative. So that's how you do the force summation. N is positive, W is negative. W is positive, N is positive. Okay, so that's how the force summation is done. All right, so that's just an example. The video is not playing. I'm not going to adjust. Okay, so it's looping the loop. All right, so this is one of those problems. What is the minimum required speed in order to complete the loop? All right, so this is good for college as well as university physics students. For university physics students, I may come up with a question just like that, except it's going to be a little bit more involved. So this sort of problem requires a little bit of an understanding of what's going on. All right, so I'm setting up my coordinate system. This is my radial axis. This is the x-axis. Right at the top, I got two forces. Both of them are pointing towards the center. All right, so they will just add up, and the squared is going to be my net centrifugal force. All right, so if you're interested in the minimum required speed, at the minimum required speed when you're upside down, okay, and it says it here also, at the minimum required speed, the lowest required speed, you will feel weightless, because the trajectory of your motion at that point is going to match the curvature of the inside of the wall. So which means that N is going to be 0 at the minimum required speed. So you can solve for the minimum required speed. And you come up with an equation. All right, so this is straightforward, something like that, but it requires a little bit of an explanation. All right, so this is more like college physics level problem. All right, so for college physics students, now I want you to focus on something else. Yeah, let me just stop there. I'm more interested in the pendulum problem. All right, so for college physics students, you will get a variation of this problem. Come on, college physics students. All right. All right, so here's the problem for it. It's the pendulum move regarding those 5 people. They said that they were going at 80 miles per hour at the bottom of the arc. This is the radius of the arc that you're looking at. So that's the same as the length of the cable. Approximate weight of 5 people is 900 pounds. So what is the amount of tension being induced on the cable? All right, so you will have a problem similar to this. So these guys picked a cable that can handle up to 4,000 pounds. All right, so that's what you got. So listing is done in terms of whatever's given. Conversions are done to the metric units. I got the mass by moving the decimal to the left, so the weight can also be expressed in terms of its mass. Okay, so I'm done with this. The listing is done. Okay, so the algebra now. Okay, so sum up all the forces along the radial direction, which is this direction. T is up towards the center, positive. W is down away from the center, that's going to be negative. So the net centrifugal force is mass times acceleration. The centrifugal acceleration is right here. All right, so add W to both sides. That's the mass, that's the weight, and that's it. So come up with an expression. Weight is given, the mass is something that you calculated, V is given, I is given. Out of that, you got the tension, and that's the end of it. All right, a couple of conclusions here that you need for the multiple second of the test. So the tension depends on the weight, and that also depends on what's going on with the mass. Remember, mass has inertia. If you're not moving, that inertia is included within this weight. If it's moving, though, it's going to be sensitive to how fast you're moving, right? So faster you go, the larger the tension is. So this term gets added onto your weight. All right, so just remember the conclusion. All right, in this case, the tension that we come up with is it's going to be what, 2,800 pounds at the end. All right, so it's going to be 2,800 pounds. These guys picked a cable that can handle up to 4,000 pounds. All right, so which means that they've done the computation. So they need this tension that they were going to induce was going to be about 3,000 pounds. They picked 4,000 pounds just to be on the safe side, except the harness broke, obviously. So that's the reason why it's for those guys. All right, so that's pretty much it. All right, so a couple of more questions. So Ferris wheel, the person is sitting on the bathroom scale at the highest point. Okay, does the weight of a car matter? No, it doesn't matter. Obviously, larger the mass is, the greater the frictional force is going to be. So the frictional force is going to be directly proportional to the weight. So the Ferris wheel, this person, it's moving so fast that on top of the motion at the highest level, the scale is going to reach 0, which means that the person is feeling weightless. So you will have to identify the forces acting on the person. If it's at rest, the person is going to have weight. Sitting on a scale, there's going to be a normal force. If it's moving so fast that you're feeling weightless, and it's going to be 0. So which means that the only force which is going to be directed towards the center is going to be the gravitational force. All right. So the force is going to be 500 newtons. All right. So what happens to the tension during a pendulum move at the bottom of the arc? Does it increase, decrease, or stay the same? Well, at the bottom of the arc, because this thing is moving, the tension is going to be more than the weight, obviously. So faster you go, the larger the tension is. So that's as far as it's going to go.